we are talking about valence bond theory, treatment of valence bond, valence bond theoretical treatment of the dihydrogen molecule problem. We have written Heitler-London wave function as a product, as a sum of two terms. One is, this is your Heitler-London wave function, and psi 1, the first one is psi a1 dot psi b2, which means electron number 1 is in the 1s orbital of atom A, electron number 2 is in the 1s orbital of atom B. Psi 2, the second term, is psi a2 psi b1. So, we have just interchanged the electrons. So, electron number 2 is in 1s orbital of atom A, electron number 1 is in the 1s orbital of atom B. And when we write this, we are remembering that electron number 1 originally belonged to atom A, electron number 2 originally belonged to atom B. But then, as you know, electrons are indistinguishable, nuclear indistinguishable. So, once the molecule is formed, there is no memory, you do not know which is from which, but you have to write the complete wave function to denote the situation properly. Then we said that we wrote Schrodinger equation using Heitler-London wave function, and in the usual manner we set up this secular equation. We have also simplified the secular equation a little bit, and we have arrived at the concept of overlap integral, where this is an integral which depends on the extent of overlap of the two wave functions involved in bonding. Okay. Next we said that we have to now evaluate the other integrals h11, h12, h22, h12. Okay. That is what we are going to do now. We start with h11. So, to find out what h11 is, I hope you remember what h11 is. h11 is simply integral psi 1 h psi 1, where psi 1 is this wave function that contributes to the first term. We do not know the coefficients yet, we will come to that later, maybe in this class or maybe in the next. So, this is what it is, but in order to proceed with h11, first thing we need to know is the Hamiltonian, and remember we had written the Hamiltonian earlier. Here all we have done is we have written it in atomic units, and we have also done something else. We have clubbed these 1 electron wave functions. You see, in the first bracket what you have is minus half del 1 square minus 1 by r 1a. 1a means electron number 1 and nucleus A, separation between them. So, this is the Hamiltonian, 1 electron Hamiltonian for electron number 1 in atom A. Similarly, the second one is the 1 electron Hamiltonian or electron number 2 in atom B. This term here is minus 1 by r2a. What is that? Electron number 2 and atom A. This is electron number 1 and atom B. Okay. I might as well have written it there, but it would have been a little messed up, that is why we have written it out here, because we want to separate the 1 electron Hamiltonians. Then this term is for electron-electron repulsion, this term is for nucleus-nucleus repulsion, and do not forget capital R is a constant for every calculation that we do. We can do the calculations for given fixed values of capital R. We do not vary it during a particular calculation for electronic energy levels or electronic wave functions. Okay. So, this is your h11. I do not know why I had to write it when it was written it here anyway. Okay. So, this is your h11 in the expanded form. I have written the form of psi 1, I have written the wave function, and this is what we have got. Now, let us take them one by one. Let us worry about what happens when the first 1 electron wave function operates on the when the first 1 electron Hamiltonian operates on the wave function here. Okay. Psi a1, psi b2, psi 1 is what we are talking about. So, I have made a little bit of a mistake here, because I have forgotten to written psi in the left hand side. So, I will just write here also you have psi 1, please do not forget, and this whole thing, sorry, this is getting a little messed up. So, what is this Hamiltonian operating on psi b2, psi a1, psi b2? This Hamiltonian, if you remember, is, I can write it like h1, 1 electron Hamiltonian for electron number 1 in atom A. So, I will write it as H1A, that operates on psi A 1 psi B 2. So, since this H1A Hamiltonian is in terms of electron number 1, this psi B 2 is going to be a constant and it comes out. So, I can write it as psi B 2 small h 1A operating on psi A 1, and that is what I have written here. Well, one more thing, this gives me the energy of 1s orbital multiplied by psi A 1. Okay. That is how I have arrived there. Perhaps there was no need for me to do every step, but just in case. Okay. So, this is what I get. In atomic units, that energy of 1s orbital would be minus half. So, I write minus half psi A 1 psi B 2. I get a nice Schrodinger equation, eigenvalue equation. So, in this expression for H11, first of all this H11 I can write it as a sum of all these terms, right. So, the first term turns out to be half, is not it? So, if I left multiply by psi A1 psi B2 integrate over all space, then I get the first term in H11, that becomes minus half, right, because what you have inside the integral is integral psi A1 over all values of r, integral psi B2 over all values of r, they are individually normalized. So, that gives you 1 minus half. So, this gives me minus half. Similarly, you can do an exactly similar treatment for electron number 2, you get minus half here as well. So, I can take those out and the expression I get is 1 plus integral psi A1 psi B2 left multiplying, the operator is minus 1 by R2A minus R1B plus R12 electron repulsion plus 1 by capital R nucleus repulsion, this operator operating on psi A1 psi B2. There is no easy way of evaluating this integral. So, since there is no easy way, what we will do is we will just write it, we will give it a name like what we did for many electron atom, remember, and like what we did for H11 for that matter. So, I will give this a name, this name is J, and we will see what J is in a minute. So, we have got H11 to be equal to minus 1 plus J. Just show you that once again, H11 is minus 1 plus this whole integral is written as J. So, I have got H11 is equal to minus 1 plus J, and this is what J is. This J is called Coulomb integral. We are already familiar with Coulomb integrals. So, I think we can guess why it is called Coulomb integral, but we will work it out. Why is this called Coulomb integral of all things? Well, before going there, let me just say that H22 is also equal to minus 1 plus J. Well, the only difference between H11 and H22 is that wherever there is 1 you write 2, wherever there is 2 you write 1. So, it will not make any difference in the final form, especially when you consider that the integral is actually a constant J. Okay? Constant means it is dependent on capital R as we will see, but for a given value of capital R it does not depend on which function you use. H11 and H22 will be the same. Great. So, now let me expand and write J as a sum of 4 terms. First one will be minus psi A1 psi B2 1 by R2A psi A1 psi B2 integrated over all space. In the second one everything is same, instead of R2A I will write R1B. In the third term everything is same, instead of R1B I write R12, and in the last term again just instead of this in the middle I write 1 by capital R. Sorry about the overlapping lines, this is what we get. So, now what are these? What are these? So, this thing first one again double integral, right. So, since I have 1 by R2A, I cannot take psi B2 out, but I can take psi A1 out of the and write it as an integral psi A1. Yeah, this thing is a double integral and the two integrations are in terms of coordinates of 1 and 2. The integral in the coordinates of 2 would be integral psi B2 1 by R2B. I made a mistake somewhere here. I think I have written this first. This integral has been written first, sorry about that, right. This integral has been written first and then we have taken it out. So, you can just go ahead and expand this. So, these two integrals have changed places. So, everywhere we get a product of an integral of a triple product involving some separation between nuclei, or well, first one is separation between electron number 1 and nucleus B, second one is electron number 1 in nucleus A, third one is electron separation, fourth one is nucleus separation. So, in the first one I get, when I simplify the double integral, I get integral psi A1 dr out, this will be 1. Similarly, this integral psi V2 will be 1. We do not simplify this, and here 1 by r will come out, and this double integral again becomes product of integral psi A1 and integral of psi B2 both of which are normalized, and so both of the integrals are equal to 1. So, what do I get? The first one becomes minus psi B2 1 by R1b psi B2. Second one becomes minus psi A1 1 by R2a psi A1, integral over all space of course, plus we get this complicated integral, and finally we get plus 1 by r. This 1 by r for whatever reason has gone up, it should come down, but that is okay. Alright, so that is J. Now see what is the significance of these terms. We have encountered this kind of integrals earlier, have not we? Psi B2 product of psi B2 or psi B2 square by R1b. Did we not say that that is the Coulombic field for electron number 2 at the position of electron number 1, and is it not just the other way around here? So, these first two terms are essentially for electrostatic attraction between nucleus A and electron 2, nucleus B and electron 1, okay. And the third term is the electrostatic repulsion between 1 and 2 obviously, and the last term is electrostatic repulsion between the nuclei AB. So, all these are essentially Coulombic interactions, electrostatic interactions. So, this goes this is called a Coulomb integral. Again, using elliptical coordinates, one can work out the expression for Coulomb integral, and it turns out to be another exponential decay in capital R internuclear separation multiplied by another polynomial in internuclear separation. When we plot it, this is what we get. Remember the polynomial we got for S earlier, in case of 1s orbital all the values were positive, right, it became 0 at capital R equal to infinity. Here however, since there is a minus sign here and a minus sign here, for smaller values of capital R, you see there is, it goes down. First of all, it starts with negative, with 0, then goes negative, reaches a minimum and then goes up. So, if you have seen the potential energy curve for a diatomic molecule, then roughly the shape is something like this, right. So, we are slowly getting there. So, this is Coulomb integral. So, J is Coulomb integral, and we write H11 and H22 in terms of this Coulomb integral. What is H12? Similarly, you can work it out. I will not do it, but I encourage you to do it yourself. It is not difficult at all once you have worked out H11 and H12. H12 turns out to be minus S square plus K. Now, what is K now? Remember exchange integral that we encountered earlier. K is actually this integral here, and here you see the main difference between this and H11 that integral we started from is this is psi A1 psi B2, and this wave function is psi A2 psi B2, right. What does that mean? For the first time, until now we were saying that when electron number 1 is in A, electron number 2 is in B, and the other way around. Here we account for delocalization of the electron over the entire nucleus, okay. The electron of A can exchange its position and be near B also, right, and reside there. That is what this tells us. So, this integral is called exchange integral, and it is very important to understand, and I think I mentioned it in the passing earlier. It is very important to understand this is a purely quantum mechanical phenomenon. There are textbooks in which hand waving arguments are given to justify this exchange integral in terms of classical mechanics. It is a wrong approach. we should never do it. It is important to understand that this is a purely quantum mechanical phenomenon, but it contributes immensely to the energies of stabilization of molecules that arise out of bonding. Okay. Now, the variation of with capital R, working this out is more complicated, so I will not even write the expression, but it is similar to that of J, Coulomb integral. It is just that the trough is much deeper. So, if I draw it very qualitatively, this is capital R. If this is J, if this is a variation of J with R, then the variation of K, the exchange integral with R, is something like this, much deeper trough. The picture is given in the textbook, but today my scanner broke down, so I could not scan it, sorry about that. But please do read the textbook, do not just rely on what we say in class. Okay. So, this is now we arrive at this concept of exchange integral, and what we see is that the energy that we get from Heitler-London treatment is expressed in terms of your overlap integral, Coulomb integral and exchange integral. How do we get it? You expand this determinant. I am not going to do it, okay, but please do try and see what kind of expressions you get. When you expand, you are going to get this will give me something in E square, this minus something in E square, right. I will just write the expression in the easiest form at least. So, I get something like H11 minus E multiplied by H22 minus E gives me, no, I do not say gives me, minus, that is a little, that would be a little easier, minus H12 minus E square multiplied by H12 minus E square is equal to 0. So, this is a quadratic equation, you expand it and use that usual formula for roots of quadratic equation, we are going to get 2 roots, right. I will show you the final result directly. The final result is something like this. Okay. Well, before that I should sorry, I forgot this step. Well, this secular equation of course has to be written in terms of these overlap integrals, or you can just take this and substitute here, and the result that you get is the 2 roots of this quadratic equation turn out to be minus 1 plus j plus k divided by 1 plus minus s square. This is one expression that you should perhaps know. So, the confusion that usually arises is where is the plus minus, here or here, remember where the plus minus is. Now, what is minus 1? Minus 1, if you remember, is the energy of these free hydrogen atoms, right. So, if I just subtract that from E plus minus, then I get delta E plus minus, that is the energy relative to the 2 free hydrogen atoms, okay. And once again, since my scanner broke down, I am going to draw the same kind of diagram here, not exactly same, some difference will be there. Sorry about the poor quality of drawing. So, I am plotting this E energy as a function of capital R. For E plus, the variation is something like this. Sorry, bad drawing. Even for me it is unacceptable. Zero, when it is very far away, coming close, goes down, then turns around, goes up and something like this. Okay, this is little better, E plus. What about E minus? I think you know up to this whatever we said, I am sure you knew all these things, but this is something that might be new for you. E minus is simply this. I will draw from the other side. E minus is just like this. What does that mean? That means that when you take plus, then you get a minimum in energy, that is this value of capital R, this is your equilibrium bond length. However, when you take this minus combination, then you get you just get repulsion, you do not get any stabilization at all. Okay. One more thing, I wrote E, that may not be very accurate. Let me write. Actually, this is delta E, please do not forget. So, this is the kind of plot we get. In one case, when I use this plus combination, there is stabilization, and in the second kind of energy we get an increasing repulsion as internuclear separation keeps on decreasing. Okay. So, what does E minus stand for, what does E plus stand for? We will come to that. Okay. So, this is what we get. Now, before we address that question, what does this, what is the meaning of that uniform increase, what is the meaning of going through minimum? Let us come back and discuss the wave function just a little. There is a little more complicated way of doing it. If you read Macquarie's book, they have done it by, or they have not really done it, they have given you pointers on how to do it from the expression for energy. But I prefer to do it in a simpler way. It involves less mathematical manipulation and more common sense. So, that is why I like it. See, have a look at this equation, C1 psi 1 plus C2 psi 2. Okay. What could the values of C1 and C2 be? First of all, coming back to that question, what is the ratio of the magnitudes of C1 and C2? What is the meaning of this? So, C1 square. What is the meaning of this mod square of C2? If you remember, they give you the contribution of psi 1 and psi 2 respectively to the total Heitler-London wave function psi. Is there any reason why this mod square of C1 and mod square of C2 should be any different from each other? There is none. So, actually this should be equal to each other, and we work with real complexes here. So, I can write C1 square equal to C2 square. So, C1 equal to plus minus C2. Okay. So, I can write C1 equal to plus minus C2 equal to C also. So, then I get two kinds of wave functions. I will write those wave functions here. Psi plus is equal to C psi 1 plus psi 2, psi minus is equal to C psi 1 minus psi 2. And the good thing about working out that problem in Macquarie's book is that you can see that this psi plus corresponds to energy E plus, where you got that minimum. Okay. That is the only thing that we are not doing here today. Okay. Now, the next thing is to find C, and the way to find C is very simple. Integral psi plus overall space equal to 1, normalization condition. So, I can write C square integral psi 1 plus psi 2 multiplied by again psi 1 plus psi 2 over all space is equal to 1. So, C square multiplied by integral psi 1 over all space plus integral psi 2 psi 2 over all space, and when I am writing this I am actually cheating a little bit, right, because there are 2 integrals, remember. So, I am actually not showing you the step in which I get rid of 1 plus integral psi 1 psi 2 plus integral psi 1 psi 2, that is equal to 1. Okay. So, simplify this, and to simplify this you will have to put in this psi a1 psi b2 psi a2 psi b1. You can work this out, we have actually worked these out already earlier, so I am not doing it again. We are going to get S. So, C is going to be 1 by root over, maybe I should write C plus and C minus, C plus will be equal to 1 over 2 plus 2s, 2 plus s square. Similarly, you can work out the coefficient for C minus also. Okay. So, this way we have completely defined the wave functions and we have found the normalization constants. So, I have not really worked out this C plus C minus, that is homework for you. You can of course check with the textbook. Now, we go ahead and say something else. See, we have got 2 things. One is 2 wave functions, right. One wave function is something like psi 1 plus psi 2 multiplied by C plus, which we have worked out, or rather you are supposed to work out, and the other one is C minus multiplied by psi 1 minus psi 2. So, if I write this out, what do I get? C1 multiplied by psi a1 psi b2 plus psi a2 psi b1, and this is plus, this is minus, C minus, psi 1 is psi a 2 psi b, no, what am I doing? Psi a 1 psi b 2 minus psi a 2 psi b 1. Now, I ask you to remember something that we had discussed when we talked about many electron atoms, many electron atom wave functions. Remember the spin orbitals. Remember that the total wave function including the spatial part and the spin part for fermions has to be antisymmetric with respect to exchange. So, see the first one, this is symmetric with respect to exchange, is not it? If you change the labels 1 and 2, it does not change, but this one is antisymmetric. So, what will be the corresponding spin wave functions? For psi 1, since it is symmetric, it has to be associated with the antisymmetric spin wave function alpha 1 beta 2 minus beta 1 alpha 2. Alright. Let me just write N1, overall normalization constant. Remember, if for 2 electron systems we said that you can have several spin wave functions. First is electron number 1 can have alpha spin, electron number 2 can also have alpha spin. Similarly, both can have beta spins, but if you write alpha 1 beta 2, you cannot write it by itself, because 1 and 2 are indistinguishable. So, you have to write either plus or minus alpha 2 beta 1 as well to account for the fact that you do not know whether it is alpha 1, whether it is electron number 1 or electron number 2 that has alpha spin, whether it is electron number 2 or electron number 1 that has beta spin, right. So, both are required. Now, see, if you interchange 1 and 2, then the first 3 wave functions do not change, the last one with the minus sign that changes sign. So, that is the only antisymmetric wave function. So, this wave function, this spin wave function would be associated with psi 1, which is symmetric with respect to exchange, and the other one maybe I can write N2, the psi 2 will be associated with alpha 1, alpha 2, beta 1, beta 2, alpha 1, beta 2 plus beta 1, alpha 2. We had encountered such things when we talked about the excited states of helium atom, remember. So, similarly, so 3 wave function, this is the triplet state, and this one there is only one wave function, this is called the singlet state, right. So, singlet and triplet, this one if you remember goes to an energy minimum. If I plot delta E this time versus R, then this kind of plot that we get is for the singlet state, and the other plot that we get, I think I used exactly opposite in color, but that does not matter. The dissociative plot that we get, this is for your triplet state. What does that mean? That means that for according to VBT, for dihydrogen H2 molecule, the singlet state has an energy minimum. However, triplet state does not. Okay. So, ground state is singlet, triplet state is dissociative for hydrogen, and that makes perfect sense. Okay. So, you see we can actually make significant advances using valence bond theory. At least for hydrogen we have been able to do it very nicely. What are the things that we have not accounted for? Delocalization and all, yes, of course we have not. Another thing that we have not accounted for so far is possibility of existence of ionic forms. See, this kind of resonance can be there, and I am saying resonance only because I am working within the ambits of valence bond theory. So, these ionic terms can make some contribution. Of course, if you have studied resonance, you know that they do not make too much of contribution. That is why in the wave function we use the scaling factor. Remember scaling factor that we used in case of variation method, that lambda that we brought in as a regulator. If you increase lambda, then the change is more. Yeah, well, even perturbation theory we use lambda, we bring in a similar lambda here, and we say that this is a small number by which we multiply, and that gives you the small contribution of H plus and H minus, and what you could do is you can use that as a variational parameter and find the minimum energy. Okay. So, does this help? Is this required? Does it help? This module is becoming a little longish, but please bear with me, we are almost done, we will complete this discussion. So, let us complete this discussion with a comparison with experiment. What you see here, and I am not showing the entire curve, only near the equilibrium, because in experiment you cannot really get the entire thing. This is the kind of energy that you get using experiment, and the experiment gives you an energy value of 458 kilojoule per mole, stabilization energy, there is a minus sign, and the equilibrium bond length is 74.1. And I do not remember if I said this, Max Planck had said that experimental results are the only truth, everything else is poetry and imagination. So, this is the truth. Whatever theory we do is poetry and imagination to try and match this experimental result. What are we doing here? We are trying to use this kind of wave function, and we will see what happens when you bring in terms one by one. First, let me show you the plot for uncorrected wave function psi a psi b, even that has an energy minimum, okay, but very shallow. So, this gives you a stabilization of 24 kilojoule per mole only compared to 458 kilojoule per mole, and the equilibrium bond length also is much longer, 90 picometer compared to 74 picometer, not so great. So, but then we know this is a bad wave function, right, because we started our discussion with our Heitler-London wave function. When we use Heitler-London wave function, we get a dramatic improvement, a dramatic increase in stabilization energy. From 24 it goes to 303 and equilibrium bond length becomes say 86.9. So, dramatic improvement in stabilization energy compared to uncorrected wave function, a little bit of improvement in the equilibrium bond length as well, but well good but not good enough. So, what we can do is we can bring in something like shielding, because after all there are 2 electrons here, 2 nuclear here, some kind of shielding will be there. So, when you bring in shielding, there is a further improvement. From 303 you go to 365, which is a little bit of improvement compared to what we had upon going from uncorrected to Heitler-London wave function, but the remarkable improvement that you see is in the equilibrium separation, equilibrium bond length. From 86.9 it goes to 74.3, which is more or less the actual value. So, shielding is an important role, because there is shielding, the nuclei can approach each other. Shielding means the electrons actually shield the nuclear charges from each other. So, that is why nuclei can come closer to each other than they would have otherwise. And finally, when we bring in our ionic terms, is there any improvement? Actually there is. Actually the internuclear separation gets a little worse, but what we see is energy goes from, stabilization energy goes from 365 to 388, significantly closer to 458. Even that is not close enough, I agree, but much better than what we started from. Okay. So, this in a nutshell is our valence bond theoretical treatment of dihydrogen, and this can be expanded with approximation methods to other homonuclear diatomic molecules, and we can try to handle homonuclear heteronuclear diatomic molecules also. Okay. That is one part, we will not go into that, but I hope you can believe me after this discussion that it can be done. Next, we want to discuss what happens in polyatomic molecules. What is the major difference between polyatomic molecules and diatomic molecules? Diatomic molecules can only be linear, polyatomic molecules can have many different shapes. So, in the next class we will have a brief discussion of shapes of molecules, and then we will say that see, we do not have atomic orbitals that can sustain those shapes. How do we generate orbitals that can sustain those molecular shapes that are determined by VSEPR? By invoking a concept called hybridization. So, in the next 3 or 4 classes we will talk in detail about sp, sp2, sp3 hybridization. We will also talk about hybridization in which you get non-equivalent hybrid orbitals.